Alrighty then, let's get started. This is the time of the quarter when the attendance in the classroom kind of nosedives because of illness. What did I read this morning? This is the sniffliest week of the year or something about this is where everybody's got the colds and whatever. Today's exercise with this kind of a crowd will be short and sweet. We are going to talk about rates, the concept of rates being useful for abrupt climate change. In other words, we want to talk about abrupt, how fast are we talking about? So what we're going to do is go to the geologic record, look at a series of examples. We're going to figure out what kinds of temperature rates are possible or have happened in the past. We're going to compare those rates to predictions for the future. And so this gives us some idea about how fast things might change. And the implications for that are a little more, are where we're going with this. Before I get started, any questions that might be arisen for the rise. You may have noticed that because the last unit in this unit is longer than the 3 days, that the first exercise is kind of low point, but then there's more exercises, so effectively we're getting more points. So just keep plugging away at them and you'll be done. All right. I'm going to comment on the global population. I'm just going to talk about a societal business for a bit, and then I'm going to look at 4 case studies, some of which most of you probably picked up in the assignment on finding abrupt climate changes for today, some of which you may or may not have gotten. But I want to work with these 4. I'm going to present a mini lecture on them, and I think what I might do is, basically the assignment is to calculate these rates. So I'm going to go ahead and do on one topic, and I'm going to turn you loose to actually calculate it now, and then you got it done. So you could easily you can have basically this assignment done before we leave class. All right, so I'm going to walk through incrementally those. Does that make everybody see where I'm going with that? All right. A slight diversion that is not in your lecture notes, because I just was aware of it at lunchtime, is the US just published something called the Fifth, and they're about every 5 years, National Climate Assessment. This is this is a US government thing, in contrast to the IPCC, International Panel on Climate Change, which publishes them a little less frequently than that. But this is focused on what is happening to climate and the societal impacts. I haven't had a chance to digest this, but we'll see I'll be drawing some material out of that. It's the kind of thing where they're designed to give the general public or policymakers sufficient information to proceed. And what they do is they carefully talk about what they think and how they assess probabilities. The world's going to stop turning tomorrow, highly improbable. The sun's going to come up in the east tomorrow, highly probable. So they have a quantitative probability of it. Anyway, it's something that might be aware of if you wanted to. I saw at least a half a dozen news blurbs about this report because it came out this morning. And so there you have it. You'll probably see something in your blurb. Last year, exactly at this time, was the day of what they call the day of the 8 billion, because that's estimated to be the day that the global population went over 8 billion years, and that's sort of a mythical number, but it did. And one of the interesting things about this is that a lot of associations plot of population over time. And one of the things I've discovered is the older you get, the more you think about history. And so I like to compare the year I was born-ish to the population of the globe at that time, around 3 billion. And it took a long time to get to 3 billion people. It didn't take all that long to go from 3 billion people to 4 billion people, to 5 billion, to 6 billion, to 7 billion, to 8 billion. And in the bottom line, folks, that only accelerates or amplifies this issue of climate change. Far more, I mean, it's almost 3 times as many people alive in my lifetime. How are we accommodating that? And what's going to happen if the baseline conditions change? Well, I'll leave that up to your discussion. I mean, it's a gnarly question. And then to give some sense of this is from last night. This isn't the most current one. You can get to this thing and you can see the numbers change. What's really interesting is the sort of the, okay, this is population growth. All right, so this is global. So a quarter of a million people born today, but only 120,000 died. So the net's 150,000 growth. Or if we talk about how much, 116 million people born today, but only 52 million of them died. So obviously that's a net increase of 63 million people. How many cities in the world have a population of 63 million people? 0 yet. Another way to think of it, how many days on a daily basis would it actually get up the population of Cincinnati? I understand this is global and I'm talking comparison. Anybody know what the population of Cincinnati is? It's actually going down. It's about 300 and some odd change. So you can populate Cincinnati every couple days, 2.5 days. You can make the city, you can grow a city the size of Cincinnati every couple, the number of people that are living in it happens every 2 days. Any comments on that? You want to make a comment on that? You were aware that the planet population was 8 billion?
I knew like it hit 8 billion. I don't know what year on this.
Yeah, it was almost exactly a year ago today. In fact, I mean, that's why I left it in here, because I think it was the 15th. Okay, it was tomorrow. The lady in the green shirt. A new Cincinnati every 2.5 days? How are you going to deal with that?
I feel like there's resources are going to run out really quickly.
Resources are a challenge, aren't you? And that's an interesting thing, because some resources might be more infinite or at least larger stock than others. So if we had a magic ball, would we dare to gaze into the glass ball and find out which resource is going to run out first? Would you have enough nerve to gaze at that?
Yes.
Buy stock in it. All right. Any statistic on here grab you?
I mean, it's just high.
Big numbers, incomprehensible numbers, of course they are. That's why the thing like size of the cities of Cincinnati doubling are probably more effective than the raw numbers. Okay, any other comments? Rates. Mundane, we're going to just deal with rates. I'm going to talk about the last century. So the most real, the current warming trend. And the graph that you see all the time is 1880 to basically this year, a couple years ago. And they always like to cleverly put it in blue and red. And why would they put it in blue and red? I mean, it's just raw numbers. Why do you think they
Like negative and positive?
Well, negative and positive is sort of an arbitrary, it's an average. And so this is a change from some average, and it's positive and negative. This is called anomaly math, and we've seen a bunch of them. They're useful to trends. They don't tell you the absolute temperature of the globe, but they tell you the trends. And so why do they put one in blue and one in red? Which side of the average are the red values on? The positive side, the warmer side, and the blue on the colder side. When I plot up a lot of my data about warm times or cold times, I use the same trick, blue and red. And so we can see that there's some sort of trend here. Now a trend is a difficult thing to pick. Exactly how do you pick it? And part of that is because there's an interval in the 40s up into the 50s where a warming trend got interrupted a little bit, and then it came back. And so the lady with the red, whatchamacallit, if I ask you right now to calculate the rate of temperature, because that's what this is all about, how fast did the temperature go up, what would we take? Would we take there to there? Would we take here to here? Would we take here to here? In other words, you could pick different starting and stop points and you're gonna get a different answer, right? Which,
From 0, maybe from that middle line. From 0, the middle line.
you'd wanna go from 0?
Mm-hmm.
Would you go from the 0 here? Well, but the 0 is all over the place. So which 0 do you wanna start with?
What are we trying to find?
We're trying to find out how fast climate can change, or how fast is it changing. So would it be, if we, remind me what rate is?
How like fast or slow something?
Fast, it has change, it's a change though, right? It's a change over the value versus the change over the time, run versus run. So it's slope. High rate, low rate. So if I did this slope, is that a high or a low value?
Pretty low.
Well, it's lower than that, isn't it? Here, it's not warming much according to this. In fact, for this period of time, it's actually cooling from 1880 to 1920. I'm averaging these out because we can do that. But here it's warming, and here it's warming. So the gentleman in the white shirt, where would you pick for, if I, look, one of the homework exercises is calculate the rate of the last century. Where would you pick your value?
The lowest point on the blue side and the highest point on the red side.
Like this?
Yeah, so it'd be like a common trend line.
I'm sorry?
It'd be like a common trend line, so it'd be the closest.
Technically, that's also a trend line, which is rate, which is a fancy term for that. All right, so is that gonna give you, but if I wanted to do it the other way, I could get a lot lower rates too, right? You're saying take the two extreme values. And so exactly what does that give you? It gives you a rate, but how would you?
Average.
Does it give you the average, or it gives you the fastest rate over that time as well?
Should be the average like this.
Well, there's no way for my ruler to really fit anything that's much faster than, well, maybe that, right? But your suggestion would be that the gentleman way in the back, how would you pick that?
I would take like the temperature from 1880 and temperature from 2020 and use those as like the starting point.
So you take the whole thing.
Yeah.
All right, and if I were to tell you that the assignment was to take the rate for the last century, would you modify that?
Then I guess I would be starting at 1920.
Cha-ching. 1920. What is that thing doing? So 1920 to here-ish, right? So all those numbers are slightly different, which is interesting, but we can pick one. All right, so it's the rise over the run, a rate. In this case, is how much temperature difference versus how long did it take. And I'm going to ask you to calculate for all of these 3-4 examples, the rate per century, temperature change per century. We'll just normalize it so it's the same thing. So, for the last century, let's go ahead and calculate the rate. Do it right now, and you got homework 1. You want to see the assignment? It's a beauty assignment. Build a table, rows and examples of temperature range, and the source of information. Put in the 4 rates of change, calculated. This is all just building a table of data, which we can do right now. There's a little more analysis in these. Okay? So I want to be sure everybody's on the right ballpark with the numbers before I send you off. So last century then is gonna be the temperature change. Do I need to know the absolute temperature to do the temperature change? Gentleman there, do I need to know the absolute number, or can I do it with this?
I think you can do with that.
Because this is tenths of a degree C. It's the change. So that's all I care about. I don't care if it's 57 or 32. I'm interested in the change. So what are you going to pick for the beginning year?
I'm gonna pick 1920.
You're going to pick 1920. And do we want exactly that 1 year?
Yeah.
All right, so what's that number?
Negative 2.3 or something like that.
2.5 maybe.
5, yeah.
0.3 would be about here. All right, so we got another one. We got a first number. What's the number for the ending value? What number do we want to pick for the end? Excuse me? We're calculating the rate for a century. We're going to start in 1920. We should have gotten 1923. We'll go 1920. What's the temperature in 2020? Here's this. You gotta pay attention because the stick is curved. So what would you pick as a number then? Maybe a little more than 0.8. There would be 0.9. Let's split the difference. Maybe 0.85. Okay, can everybody do the math now? There's a negative sign in one value and you want the difference. Be sure you don't add when you're trying to subtract, or the other way around. Minus 0.35 plus 0.85, right? Number?
Did you do 0.35? I thought we did 0.25.
It was negative.
Yeah, negative.
For 1920? I think we did, you're right, 0.25, great. With 0.25 and this one, what do you get? 1.10? 1.1 degrees Celsius, everybody got that? Make sense? What's my rate of temperature change then? With that data.
Wait,
I'm sorry? Go ahead.
I'm calculating.
Can get a little confusing.
0.3.
Okay. The lady just said the temperature change was how much?
1.1.
1.1 degrees Celsius. Is that right? 1.1 Celsius because we didn't take the average, we took the exact year.
Yeah.
That was down here someplace and up here. So we've got a number and we want it per century, right? How many years did we estimate that for?
140 years.
100 years. And that's 1 century, right?
That's 1 century, but wait, what is the time for the whole process for about 1.1 degree temperature?
Well, we took, if you did it technically, the rise of the run is the difference in temperature rise versus the difference in the time. So if I subtract the 2020, excuse me, I subtract the 1920 from the 2020, that's my 100 years, right? So in this case, it's what I'm looking, it's the same unit I'm looking for per century. So the math's trivial, right?
Yes, I see that. But if we choose the 90-20 to 20-20, so that it will be. That will
Anybody know what these are? Okay, good. We won't do that class.
Yeah,
Excuse me.
that will be 1 and 2 and 1 minus 0.4, so that is 1.4. That's for the year range in the 90-20 to 2020.
But we want the total change, right?
Yeah.
So we're gonna have this much change plus that much change, which is more than a degree, it's the 1.1. That work? Did I get it right?
Wait, which year we start?
1920,
90-20?
yep,
Yeah, so that will be.
to 2020,
Yeah.
100 years.
That will be the temperature of 2020, and then we minus the temperature of 90-20.
And the way this scale is set up, it's minus a minus number.
Yeah.
So
So that is plus. I know that. Yeah.
It's 1.1 degrees per Celsius. All right, so this is a gift because we had it scale in a century. From here on out, we're gonna have to calculate the number of centuries. We ready for those? Let's do it. I'm gonna go back in geologic time. And I'm not necessarily following the order you're supposed to do it in. But there is a study that looked at the last glacial maximum, the end of the last ice age. There's going to be two different examples from the end of the last ice age, by two different groups using different approaches. Guess what? They're going to get a different answer. Group one looked at the sea surface temperature since in the last basically 24,000, 25,000 years. And we want to compare that with a modern rate. So here's a set of folks, they did a lot of reanalysis of the temperature. There's no thermometers 20,000 years ago, so you need proxy records. So they look at some chemical proxies and recheck their calibration of those. And what they did was assemble a large data set through the globe. And what this tells you are the different ways they did it. They combined 4 different techniques. We don't need care what they are. And then they looked and they said, geez, there's some places, some latitude, South Pole to North Pole, that have more data than other places. These data points are not particularly high. These data points are non-existent. So this is a latitudinal distribution. And then they did the same thing by age. They said from 24,000 to 0, there's this many of the yellows, heck numbers used. There's this many of the blues used. There's apparently not too many purples, and then there's this many oranges. Okay? So, gentlemen way in the back, you have confidence in the data set.
Yeah.
They took everything they could. It's not a bad data set. We can nitpick around the edges in terms of, oh, they're missing points here, but maybe that's important, maybe it's not. They did 2 things though. They actually used the raw data, which you're presenting here, and then they used a modeling. And then they put the results in a 200-year bin, all right? And so here's the resulting data set. And here's 24,000 years ago, here's 0,000 years ago, and this is the estimated temperature. Now, almost back to you. That's not shown as a single line, is it?
No, there's like a cutoff in between.
Well, it cuts off. It's back here in the ice age, cold, gets warm, there's a little glitch, and then it's basically steady warmth. And they changed the scale over on this so that this is the little rise we just looked at before, right? So we were just looking at that thing right there. In the grand scheme of things, is that a big deal or not? the absolute temperature, maybe not, but maybe the rate is. That's what we're trying to figure out. So now, back to you. I want to know where the most rapid warming is, right? So where do I take the last glacial, where do I pick my numbers? Here's that temperature.
I would say at the lowest value,
Lowest value?
then right up to where it starts leveling out. Probably right.
In here someplace?
Yeah.
Tell me where, I'm gonna come.
Okay, all right. Right there.
Okay. Lady in the back, do you agree with that pick, or would you pick something else? I wanna get the rate of temperature change. He's picked it from the coldest to the spot where it sort of goes. Does that make sense, or would you do it a little differently? Make sense, all right? Would you wanna quibble with him, whether he picked here or here? Why not? Your argument might be that probably is not gonna make a big difference. Okay, great. What do you wanna do with this bumpity bump? Ignore it, hope it goes away, investigate it? Look, there's a bumpity bump. Otherwise known as a climate oscillation. Specifically known as the Antarctic cold reversal climate oscillation. Is that gonna upset our trend? The suggestion is to go from here to here, but there's a bumpity bump in there. If we go from here, are we gonna get a higher or a lower rate? Go ahead.
Higher?
Higher because it's steeper,
Yeah.
okay? So I got two choices, a lower rate or a higher rate. Or maybe even a higher rate. Which one do you think is more interesting?
Interesting?
Yeah. They're gonna be subtly different. But I'm asking you to calculate these rates for comparison. You want the average ones, you want the extreme values. What's the title of the section? What's the unit name? Something about abrupt, right?
Yeah.
So do I want slow? So do I want to deal with slow ones, or do I want to seek out the fast ones?
See that the fast ones.
Seek out the fast ones. Do you agree with that philosophy? Just because she's sitting next to you?
No.
So where would you pick the beginning and end then? Tell me where is the starting point?
Oh wait, which one are you asking? Sorry.
Right there. So here's a time. And what are you going to pick for time? There's 18,000 years ago, but it's not exactly that. It's going to be 17 something.
Yeah, I feel like 17,000.
Do you think it's 17,000? I think those things are going to drive me nuts pretty quick. This is 20. This is 18. 17 would split this difference here. Probably just a little earlier than 18. Call it 17.8 or something. Excuse me, 18.2. Okay? Where do I want to pick my ending time? We decided to go for this. Tell me where.
So are we ignoring that bump that's right there?
Say.
Are we ignoring that bump that's right there?
Well, if we have the bumpity bump, it's not as fast as if we ignore the bumpity bump. So if I'm looking for the fastest that the world can react, Do I wanna take in the bumpity bump, or do I wanna ignore it?
You wanna, but does that mean we'd stop right before it, or just?
I think you could stop, as long as it's warming, I think you could stop. I mean, you can't stop here really, but you can stop in here someplace, right? So pick the peak of the bumpity bump. And I'll let, you wanna, somebody else, let's see, who do we need to talk to? Yeah. What's gonna be the age of the top of the bumpity, before we dive into the bumpity bump?
Probably like 13.8.
You're gonna go with 13.8, okay? All right, what's the temperature change now? Here. Give me a temperature.
Right there, like probably negative 7.25.
Depends exactly how I
Maybe
hold this,
more.
but it's 7 and a little bit, yeah?
Yeah.
All right, -7 and a little bit. Gentleman way in the back, how far did it warm up during that time? Excuse me? -3's here, maybe a tad. 3 and 1 or 2 maybe. Is that all right? All right, can do the math. Everybody can do the math now, right? You got change in time, you got a change in temperature. You got the rate. Got it calculated?
Yeah, if you're searching for like abrupt, why would you not just do the little bump? Because that looks more steep.
So you're arguing to do this bump, right?
If you're looking for the most abrupt change, yeah.
Go ahead and calculate that one. Let's do this one, and then let's also calculate this one.
Okay.
All right, so option A is to calculate this one. Option B is gonna be to calculate this one. They're gonna be close but not the same. So you wanna walk me through the numbers for the short rise here? What's the time of the start? 12
12,
and 14.
12.5 maybe, or I don't know. I can't tell.
Yeah.
Maybe 13,000.
It's 13.2 or something. I know it's 13.2 from other stuff. We'll call it
Yeah.
13.2. When did it finish?
There's 11,000.
11,000, okay? Temperature? Somebody else want to help me with the temperature? What are the temperature changes, please?
Here we have minus 3.6. Well, no, 3.5.
3.5?
And we goes to minus 1.4 or 5. Let's go 1.5.
Yeah,
So
that's 1. Yeah, maybe 3, 1.3, but sort of the same. All right, so now you've got two possibilities. Which one gives you the faster rate? We're approximating this, so, but they still could come out right. Everybody got the two sets of numbers now. We can do two. It'll be bonus. We'll make up a bonus for this. Set this up in a little table. What is going on with this? Everybody got two numbers? No? Got two numbers? Which is faster, the bumpy bump or the longer time frame?
Well, for the first one, you were saying that we start at like 18,000, but it looks like 17.
Say that again a little louder, please, so everybody can hear you.
You said the year would be like 18,000, but I thought it was more like 17,000, which changed.
Yeah, I think we picked 17.8 or something like that for this one.
Okay, 17,800.
Okay. And then I think, what was it, 13.5 or something, so we get the same, we can use that number. That's for without the bumpity bump, and the other one's the solar distance. Which is faster, the bumpity bump ride or the?
I'm still trying to calculate.
Oh.
What is the year or age for
For-
the second or the upper of the?
I think we talked about, here's 12 and 13, 14,
Yeah, 13.
and that's
We got-
13, so we said 12.7, I think. We might not have.
For the other one though, the one
For
above
this
it.
one?
The one above it.
Here.
That, yeah.
Well, let's see.
Find the difference.
It's not quite to 10. It's not 11. Call it 10.5,
Okay.
10,500. This exercise probably, it doesn't, if you pick 10.4, you're not gonna be that far off. So don't get too worried about whether you pick 10.4, 10.5. We're picking them communally, so so I can see all the same answers. If you pick a different number, it's gonna be fine. Your analysis doesn't depend on the exact number. All right, so we're still, boy, I'm saving all kinds of time. You don't have to do any homework. Get it all done. And this is not fair because this is a long weekend. You have all kinds of time to do it. This is the long assignment. So you have all this free time over the weekend. What a great day.
We have class Thursday, right?
This week?
Yeah.
Is this Thursday?
This
This is Tuesday?
This Thursday.
I have to remind the lady in the front office what day of the week it is every once in a while. Yeah, so this is a short one, so no pressure. There's always an advantage, you just gotta know how to look for it. Lady with the pink drinky thingy bee, got two numbers, two different rates?
What was the second set in terms of 10 or like 10?
10.4 or 10.5?
Yeah.
This would be this point here. We can use it for that rate, or we could probably also use it for this rate. Is that making sense? Or we could pick another number here, but we probably want to pick that 10.5. Every time I hold it up, I'm probably getting a slightly different number. If I take the same place to stop it, which value is going to give me, just by inspection, going to give me the higher rate?
I got the little bumpity bump is a higher rate.
The little bumpity bump, beyond the little bump, younger than the bumpity bump is a higher rate, and you can see that from this, just changing the slope of this, if we stop at the same spot. So double check that you get, for the bumpity bump, a faster rate than for the whole thing.
Do you know the exact numbers?
I'm sorry?
Do you know the numbers, like, of the rate?
For these things? Do I know the numbers? Not off the top of my head. I know how to calculate them.
I just wanna make sure I was doing it right.
It's a very complicated formula, you know. Yeah, it's right, it's slope. It's the slope of the line.
Okay.
I have no idea what the numbers are. I know the net effect. All right, so everybody got numbers? All right, that's good. We know which one's faster. Now, they did something very interesting in this study. And here's the answer, actually. They compared rates from different time slices. And so when they did their modeling, here's the warming rate. Here's the temperature. They're talking about now, they've switched gears, 1950 to 1980, which is the first graph they had. And so they stuck that in because they were trying to figure out for that time slice what the rate was. And they used a little more complicated graph than we did. But by picking different, so to get around that corner, they took a range of different values. Okay? So these are the rate numbers that they got for the last century. If they take, now in this thing, they actually took the rates they got, what we just calculated, basically. And it's not one number because they calculated in different places, they're gonna get a variety of numbers, right? Then they matched the reds and they stuck them on here because they're a rate, they're the slope of that line. Gentlemen, way in back. Questions about what the red lines represent? They're rates and they change a little bit, right? These are the rates they got from their older record, right? I said that. If you go through that text, this is a distribution of the rates they got from the older time. And so how did they compare the younger time versus the older time? They graphed it and they plotted those colors here. So which is the faster rate? The dark color or the light color?
The dark color.
The dark color. And the dark color is way over here. Compared to their data set, are there many time intervals that have that same rate? Virtually none. Compared to their slowest rates, how many time intervals had this? A few more, but not a significant number, right? So what would be the conclusion about the warming during the end of the last ice age compared to today's rates?
It was going to be on like the lower side. It was like negative skew.
Say that again, please. My hearing's not great.
Would it be that it used to be negative skew and now it's positive skew?
They have, but are the rates higher or lower than in other parts of their record?
They're higher now.
They're higher. So there's a primary conclusion, which is a question I basically asked you later. According to this particular analysis, by that approach, their conclusion is the rates in the modern are faster than anything they've seen in the geologic record. Okay? What do you think way in the back? Back in the corner, listen to the construction music. Is that surprising, or does that seem normal, or does that?
Yeah, I think it seems normal.
Seems normal, okay. And there is some overlap, but it's pretty minor. Okay. So that's something they did with that. We've done the termination example 1, the Younger Dryas. This is supposed to be the type section of the abrupt event. These characters have been writing lots of papers about it, and well, this is a 98 paper, isn't there? But they are talking about the climate changing in a order of decades, and with a very fancy technique, this fellow has sort of has a temperature range, and they use properties of the gas. I don't fully understand exactly what they have to do, but it's fractionation of the gases through the crystal pore space in the ice. These are not the only rapid things, but they're one of the first that actually get with the nitrogen isotopes a number that people would agree on. Okay, so this is a study. These are all first-class scientists, and here's their ring. So here's time, old time, young time. Here's the wiggly wigglies, and then here's the end of the underdrives, not the beginning, the end of the underdrives. So that's snow accumulation. This is an isotopic look. It shows that, but it doesn't really tell us temperature. This is in how much snow's falling. It sort of doubles. This is in isotopes, they change. But then the nitrogen isotopes also change at the same time interval. And this is the infamous beginning and end of the underdrives. On this graph, you can't tell the difference. If you want to make something impressive, you stretch it, you compress it, and it looks sharp. You want to make your portfolio look good. You only record the last 5 days when the stock market was going on. You don't take all of the downs and lows from 50 years. All right, so how are we going to get this? They're getting the temperature with some fancy thing, but the time scale's too coarse to do the exercise I'm asking you. Let's zoom in and look at time scale that's much accelerated. They've zoomed in on this, and now we can talk about the beginning and the end of the underdrives. Here's the same data plotted, roughly, and we want to pick the beginning and end so that we can get some sort of change. And why do I say the black line is a 5-degree change? They're fitting that to the curve. All right. Here, how do we get this one? The black line is occurring, there's the temperature range. It's starting here, and it jumps to there, and that's 5 degrees. So we don't have a temperature, but we do have to get the time, right? Who wants to help me with this one? How long is this time? So I want the time from basically here, where it goes to here. That's not very long, right?
Yeah. Let's look at just 1 unit on the scale.
Those are thousands of years. So that's 11,600, 11,700. So now we have to be, it's going to be 11,600 and
2.
and 2.
I don't think it's very accurate.
11,620.
And 3. And oh, here is 2, but I think it's 3.
Right, so there's that. There's 5, right?
Yeah.
That's 2.5. So it could be 2, or let's call it 2.5. So at the beginning of it is 11,625.
Yeah.
Okay? Gentleman in the black coat. The end of it, where do you want, tell me where to pick the end. See, this is way too long.
Oh, right there.
All right, right in
Yeah,
here.
right there.
Number is, says,
11,575.
11,500, 1,600, there's, and that's 1,600, that's 1,575. 11,575. Much, much shorter time. We have to go out to another decimal point. All right, and the temperature is 5 degrees. That's a given. Fast, slow?
Fast.
I know it's fast. How fast?
I got 10.
Excuse me?
I got 10. I don't know if that's right.
10 what? 10 thingamabobs, right?
Yeah, I don't know what the unit is.
What unit are we trying, how do you know what you got 10 of then?
Is it degrees Celsius?
Degrees Celsius, but it's a rate, so there's a time.
Oh, per. I don't think it's per year.
No, it's not per year. If it changed a half degree per year, you'd know it. I'm trying to normalize to the nearest century to keep the math, to allow comparisons. I can't make a comparison if it's 5 degrees change, if it happens in 1 year versus 10 years. I need to know the rate. So he just gave you, we just talked about, these are thousands of years, but we broke them down. How many years total was it?
50.
50?
Oh, if it's thousands, it would be 50,000 years.
The start was over here, time's coming this way. It was 16, we said it was 16 and a half, right? We agreed on 16 and a half thousand? Or is it 2.5? 16,250. Right?
I thought it was 11,000.
Excuse me. Thank you. 11,625. That's the start. That's the Overwatch plan. The ending time is 11,000, not 17.5. It's one of these little thingamabobs later, right? And the thing, a little more than a thingamabob, and the thingamabobs are 25 years. 1, 2, 3, 4, 5, 20 years. Okay? So what's the unit then?
For 25 years?
Yeah, 25 years. It's 5 degrees Celsius, that's the easy part. The chronology is the hard part here, right? I want it in a century though. These are centuries apart, right?
Would you just divide by?
Or multiply. This higher math stuff, man. It's a good thing you're not writing my paycheck, or maybe it would be a good thing, right? What do you got for a number?
Well, okay, so the start is 11,625,
Start of it?
and then the end, I thought you said 11,575.
Probably. I think we've said
That's what
those
you said,
numbers,
okay.
yeah. So that's a total of how many years? 50 years. It's a half a century.
So then.
50 years, okay.
So then that's half century, so then a full century, you get that 0.01 for half, so 0.02 for a full century,
Okay.
right?
So what's the rate then?
0.02
0.02
degrees Celsius.
per century? It's too low. It's a half a century. It's a half a century, right? We want a whole century. It's 5 degrees in half a century. It would be 10 degrees in a full century. Not doing too much math, right? But it's lucky that it's 50 years. But by 50 years, I said, all right, I want 100 years, so just double it. And then double the temperature it is. So it's 10 degrees per, yeah, per century. So 10 degrees. Did I do the math right? I'm ad-libbing this, I don't remember these things.
Keep going, sorry.
No, go ahead, what?
It's,
Yeah.
then it's 10 divided by 100?
It's
Divide
one,
the
it's
rate.
1 century. I took 50 years and I said, let's pretend that it's 100 years, because that gives me 1 century.
So it'd be 10 divided by 1.
Right, but if it happened 1 degree, if it happened this much in 50 years, then 100 years is gonna double that amount, right?
Yeah.
Because that's what I did the math in my head.
So you would go from 5 to 10.
10 degrees change
Yeah.
per century.
Yeah. So then it would be 10 divided by 1 century.
Correct. 10 degrees Celsius per century. I'd like to get that kind of interest rate on something, right?
That'd be nice.
Higher or lower than the other ones we've been talking about? A little higher. Okay, so we're starting to see some stratifications amongst all of these things. We don't have to do that one. Now, we're going to do the termination again, but we're going to do it with a different data set. We're going to get a different rate. This is a temperature estimate. I'm not going to go into all of the gory details, but it's something about glaciers. They're tracking air temperature. They are basically this line. So the glacier to be, this is actually the length, but the glacier to be this far, it needs to be this temperature. Same thing, same thing, same thing, same thing, same thing, blah. A change in glacial length, a change in temperature. The time, the way they've plotted this is pretty dramatic. One of the points of this particular argument is that this metric tracks the air temperature. Another study tracked the ocean temperature. And so what you see is, here's today, here's the peak time, so the story goes this away. And this is north-south in the ocean temperature. And so what you see are cold ocean temperatures. Cold ocean temperatures, doesn't matter where you look, and then after this time slice, you see warm ocean temperatures. So the implication of this study is not only that the atmosphere changed, but the ocean changed at the same time. I'm going to talk about this study again. It's called the Zealander switch hypothesis. This data set suggests that temperature range in that much time. Should we do the numbers? Starting is, according to their scale, is -6. The ending is, who's going to help me on this?
I don't know, I think 2.5 maybe?
2.5, okay, let's call it 2.5. 6 to -6 to -2.5 would be how many? 3.5, right? It's 3.5 degrees Celsius temperature change. The tricky part, how long did it take? Gentlemen way in the back, can you see that? You can see those numbers. Probably say no and then you're out of the game. See? Can you see them at all? All right. So, lady with the red cup. When does the start happen? Isn't it convenient of them to give you the vertical lines? So here's 20,000, 15,000, 17,500, right? 17,500. 17,000. I think they put these marks in here. How are we going to estimate that? It's on either side of this, so once we get one of these, we can just add it together. You want to cheat? Let's do this. We don't care about the absolute time, really. We just need to know the relative time, right? There's 2,500 years, right? That's 5,000, 2,500. And what percentage of that? Or is this making it too complicated?
I thought it would probably just be like 16.8 to 17.5.
Say that again, please.
Like for on the left side of the mark, I feel like that would be like 16.8 or 16.7.
16.8 for this one?
Mm-hmm.
Okay. Let's use 16.8 for this one. And what about the older end?
17.5.
Finishes at 16,800.
17.5.
Yeah, 17.5 is going to be here. So it's going to start before that. It's coming up on 17.5, so it's gotta be 4.17.5. Is that right? Time scale keeps going back and forth. 20,000, 15, 17.5, 17,500. Call it 18. 18, and then remind us when it stopped, finished. This is 17.5, 18, 17.2. 800 years for this exercise. 800 years for that temperature range. You got a rate. Everybody got a rate?
Wait, no, hold on. The start year was 16.8.
No. This is 17.5.
Oh,
So if the start year is older than 17.5. Somebody has to remind me what year we picked. 18 something. 17.5 is here, so it's a little bit more than that. I'm sorry? It's older, right? Time goes that way in this graph.
So if the start's 18, then the ending you said was.
Has to be 16.
It's gotta be 16 something for it to end. So it's gonna start 18 or up to 17, and it's gonna end in 16,000. So it's gonna be something on the order of a couple thousand. Now let's see if we can get that a little bit better. 17.5 is the same difference on either side of it. So there's 3 of those between 7. See, this is the problem. I always do it in my head in some oddball fashion. And that's 2/3 of 2/3 of 2,500. 5,000 divided by 3. 1,300 years. Call it 1,300 years. Yes, sir.
Yeah, if the graph goes down like this, do we use the rate but with a negative number, or we just use the positive one but we say decrease rate?
No, the graphs are the same regardless of which way you turn. It's the difference, right?
Yeah.
So this is 5,000 years, but if I flipped it the other way, this graph would have flipped this way, so
Yeah, sure.
it will give, the algebra will give you the same number.
Yeah, I see the rate is the same because we can change the graph like left to right.
Mm-hmm.
So what we want to calculate is just the rate. We don't need to care about is the negative word or positive word. Okay.
Well, correct. If you wanted to, but if time goes this way on this graph, our rate for warming would be this, because the temperature change was to warm.
True.
And it isn't, because this is a time thing, it can't actually go this rate. But this would be your conceptual negative rate, but it doesn't make practical sense for this particular example. Does that make sense? Yes, ma'am?
Are we calculating the rate in centuries, all of these in centuries?
No, what is the number I gave you? 15. I gave you 1,300 years, 1.3 centuries,
oh, so then,
right? You gotta keep me, you gotta watch this math, man. 1,300 years, 1.3 centuries. How many degrees temperature change?
0.0027.
For the that's the rate?
Are you wanting to like the 3.5?
You want 3.5 is the temperature change,
And then don't you
divided by 1.3.
by 1.
It's a little longer than the century, right? So we gotta cut it down. But it's still gonna be 2.7 degrees per century. So far, so good? All right, let's wrap this up so everybody can get out of here because it's a short evening. Oh man, why didn't we jump the thing? Because this is plotted on graph paper so we can see it. Did it the easy, we did it the hard way, excellent. And those are 1, 2, 3, 4, 5. That would be 5, be 50 years. All right, you can check that down. All right, so we've looked at 3 examples, the historical, the Younger Dryas, one way to talk about determination by ocean records and a big synthesis of stuff. Another way to talk about it by those glacier systems. We can reduce that all, and we're gonna go it in centuries, degrees Celsius. We've gotten some numbers. We might be a little different still because of what we picked. Put that all in a table, and we're gonna ask you to submit the table. I think he's changed the structure a little bit. And then, so there we go. That's all math. Find something that talks about the rate of change for the next century, or predictions for it. Are the past examples slower or faster than what's predicted to happen? Does that matter to you? You see an awful lot about the word unprecedented. The warming is going to be unprecedented, above. You just made a very crude estimate of how unprecedented. You agreed, in essence, with this study. Oops. This study is sort of the future. They are unprecedented in this regards. Was the estimate that you just made higher or lower than that? Warming rate, degree per century. Their fastest one was a degree per century. What did we just calculate? For the last one.
The last one?
Yeah.
I got 0.269 degrees per century.
So the one we just calculated has more extreme numbers than this. They're over here someplace. Correct?
Yeah.
Who's confused? Let's get out of here. I'll see you on Thursday. Since this is Tuesday, you tell me.